Hello everyone, welcome back to this channel. In our last video, we defined what probability is, meaning that a numerical measure of uncertainty, and it helps us quantify how likely an event is to occur. But probability in its computation is not defined by a single lens. In fact, it has evolved through multiple approaches, each offering a unique perspective on how we understand and apply it. In today's video, we will explore these different approaches in detail. Stay with me. In probability, we have four different approaches of defining probability. One is classical, second one frequency, the third one axiomatic, the fourth one is subjective, right? Where the first three are scientific approaches, whereas the fourth one is subjective, which is the world of belief. We will explain each of these approaches to define probability. At the end of this session, you learners will be able to understand the four different approaches to define probability, and you will be apply the concept to solve simple probability problems. So, what is classical approach of defining probability? When can we use it? The classical approach is nothing but when all outcomes are equally likely and mutually exclusive, and the total number of outcomes is finite. Under this condition, defining probability using classical approach is appropriate. Let us see what the formal definition says. If a random experiment, which is E, with n equally likely outcomes, right, this produces n equally likely outcomes, and out of this n into a, right, n into a or na outcomes are favorable to event a, then the probability that event a occurs denoted by PA is nothing but defined using this formula, right? In different fashion, we have seen in the previous sessions probability of A, where A, which is defined over the sample space, where S is generated from random experiment, is computed using NA over N, right? Meaning that N into A over N into S, the simple presentation, where number of elements in A should lie within this range. Recall that where NA is 0, A is said to be impossible event, right? If NA or number of outcomes favorable to A is N, then A is said to be certain event, right? Whereas if the number of elements favorable to event A lays within this interval exclusive to 0 and n, that event is uncertain event, right? That event is uncertain event. So we can generate three cases from this interval. This is nothing but to make you recall. But what the focus of this session is defining this probability of A by this n into A over n, where n into A is nothing but the number of outcomes favorable to the event A, whereas n is nothing but the number of outcomes in the sample space, where the sample space generated from a random experiment. This classical approach is originally introduced by Bernoulli and Laplace, right? And this approach is the oldest and the simplest one. Let's see one example over this one, right? If we toss a fair 6-sided die once. This is nothing but the random experiment. From this random experiment, we expect to have this sample space, which is denoted by S, which consists 6 outcomes, where this 6 is finite, right, and could be enumerated, right? And we know that these outcomes are equal likely outcomes. The probability of every outcome is 1 over 6, where I 1, 2, 3 to 6. So we assure that outcomes are equal likely outcomes where the sample space is finite. Now let us define this event as event A, B, C, and D. For example, event A is about getting a number 4. Event B, even number. Event D about getting any number, whereas event C getting an odd number less than 6. This definition of events is based on the statements and words. But this way of expressing can be reduced into the set notation. A is nothing but a set which contains only one number 4. This B is about getting an even number, so the possible interest to the event B is 2, 4, 6, where 2, 4, 6 is the subset of S, right? Now this event is nothing but represented by the set, this event by the set. So what the interest here is whether the probability in each event is computed well based on the classical approach of defining probability or computing probabilities, right? For example, probability of A is 1 over 6, where 1 is nothing but the number of elements in A. How many elements in A? 1. How many elements in our sample space? 6. So 1 over 6 is nothing but numerical number which is assigned to the probability of A, and it is valid probability. The same is true probability of B, right, is nothing but MB over N. How many elements in B? 3. How many elements in S? 6. This is nothing but 1 over 2. Getting an even number had a probability of 1 over 2. From an experiment tossing a coin once, it generates the sample space on which we define these events. This getting an even number is one possible defined event for which we calculated its probability using classical approach, and we come up with this number that is assigned to this probability now. Similarly, getting an odd number less than 6 is nothing but probability of C, N into C, N into S. How many elements? How many favorable outcomes in S? In C is nothing but 2. 6 is nothing but in the sample space 1 over 3. The same is true. This one is sure event. Getting any number of this sample space is nothing but the sample space over the sample space. Probability of S, probability of D is N into S over N into S. This same number cancelled out, we come up with 1. This is sure event. Now D is sure event because it considers all elements in the sample space, right? What if an event E is defined to be getting number 8? The probability of E will be 0 over 6 because we don't have number 8 in our random experiment produced, right? Our domain is from 1 to 6, but from its outset this event is a number out of that range. So this number 8 is not in our sample space, right? So this is impossible event now. impossible event. When we define probability using frequency approach, we need to have long-run experimentation, right? This way of defining probability is classified under the real-world definition, right? Because it requires long-run experimentation and observation, right? On the course of these all things, we are becoming to realize what the observed thing is. So, the probability of an event A is the limiting of its relative frequency, right, as the number of repetitions approach infinity, where f A here is nothing but the number of times event A occurs in n trials. Now n is number of trials, f A is the number of times that event A occurs. This can easily visualize using this example. Suppose we toss a coin 1000 times, from which, if we observe 532 heads, what's the probability of getting heads, right? This is nothing but 532 to 1000, which is this probability, right? As n increases, say up to 10,000 flips, this value will get closer and closer to the classical value of 0.5. Recall that based on the classical approach of defining probability of getting head is 1 over 0.5, right? This is fixed in any independent trial of tossing a coin once, twice, or 3 times, right? But this frequency approach of defining probability is applicable only for repeatable experiments under identical conditions, and requires a very large number of repetitions to be accurate. While the third way of defining probability is axiomatic approach. This approach is most powerful and modern approach. But instead of telling you how to calculate probability, it lays down the rules of the game, right? That any valid probability must follow, from which a number of ways of computing probability for different combinations of events can be derived. So, before getting into the derived one, let us see the 3 axioms of probability, the 3 rules of the game. Suppose S be the sample space and A be an event, right? From a random experiment E, we expect to have sample space. From this one, we define an event A. So, for this event, we need to define its probability using axiomatic approach, right? Now, this probability of A is any number associated to this probability which satisfies these 3 axioms, right? Now, probability of A is expected to be non-negative under these axioms of probability. We have one axiom or one rule which is about non-negativity of the probability of A. The second one, axiom 2, about certainty, where the probability of getting any outcome from the sample space is 1, which is sure event, meaning the probability of this event, because the sample space by itself is an event, because this S is a subset of itself. This fulfills the definition of event. So the probability of S is nothing but 1 sure event or certainty. This should be satisfied on the course of axioms of probability, right? And the third axiom, for any A and B, right, which are mutually exclusive, meaning A intersection B is implicit, meaning they A and B could not occur or could not happen at the same time, implicit, then the probability of getting either A or B is the probability of the sum of the probability of the individuals, right? This is also the third rule of this approach. And this additivity formula for two events can be extended to any finite number of mutually exclusive events that can be compactly written using this formula, right? So under these axioms we can proceed to derive a number of theorems, right? Before that, let us see some example. Verify the axioms with a fair die, right? For example, tossing a die, six-sided die, produces this outcome, where A is defined to be getting number 4. So as the probability of this one, probability of A now is 1 over 6. 1 over 6 is greater than 0, right? Using axiom 1 of this approach, probability A satisfies the first rule, right? Axiom 2 about certainty. For the whole sample space S, probability of S is 1, right? Probability of S is the number of elements in S, the number of elements in S. This is 1. This axiom or rule is also satisfied for the random experiment of tossing a six-sided die once. And the additivity axiom, let A is given by S1, B given by S1, and they are mutually exclusive because A intersection B is empty set, right? They don't have any element in common, right? So the probability of getting either A or B is the sum of the probability of these events. While the probability of getting number 2 or event A is nothing but 1 over 6. The probability of getting event B, which consists number 5 as its entry, is 1 over 6. Then this sum is equal with this one, right? So we can also generalize to 3 events, where A1 is this one, A2 by this, and A3 this one. Getting probability of getting A1 or A2 or A3 is nothing but the sum of the occurrence of each event, right? This is nothing but 1 over 2. If we bring this one into one event, for example, event A as 1, 3, 6, what's the probability of A now? This is nothing but 3 over 6, 1 over 2. Now A is nothing but A1, A2 or A3. This is nothing but this interest under one event is equal with these events in different, these outcomes in different events, right? Having understood these all things, right, we can prove other very useful factors based on the 3 axioms. So what the importance here is, it is not only about setting the axioms, but from the axioms we can derive a number of probability formulas, right? We can define and we can compute any driven probability from the 3 axioms. For example, theorem 1, probability of an impossible event is given by S1. This can be proved. Theorem 2, probability of a complement. If A complement is the complement of A, then the probability will be 1 minus probability of S1, right? We know that this is the sample space. If A is defined within this sample space, A complement is nothing but this area, this shaded area, right? A complement is this one. So what's the probability of A complement? We know probability of A, but now in this context we are looking for probability of A complement, right? Probability of A complement is nothing but we know the probability of the sample space is sure event, which is 1 minus the probability of this circle. What is left? The probability of the shaded one, right? So this probability we know by axiom 1, which is non-negative, and this one is by axiom 2, which is sure event probability of S, right? So this is a formula which is derived from those three axioms under axiomatic approach of defining probability. And we can say under theorem 3, probability of a subset, if A1 is a subset of A2, A is contained within A2, then the probability of getting event A1 is less than or equals to probability of A2, because probability is defined based on the times of the occurrence of the events, right? So this is obvious that if A1 is contained within A2, so A2 is the superset, right? This can be extended to its probability too. Probability of A1 less than or equals to probability of A2. Still, this is the super one in its probability fashion too. The same is true, theorem 4, the general additivity rule. We know the probability of A union B is probability of A, probability of B for A intersection B implicit. But without this criteria or assumption, what will be the probability of getting A or B regardless of this assumption is? This is nothing but we subtract probability of A intersection B, right? From the beginning, if A and B are mutually exclusive, this becomes 0, unless otherwise we subtract this real number from this sum to obtain the probability of A or B, right? So the general additive rule is given by 1. Was the fourth, which is subjective approach, is based on personal belief, judgment, or experience, right? For example, if I see a kind of cloudy day, wow, I can guess to highest number as today rain will come, right? I can say probability is a measure of how confident an individual is that an event will occur. For example, a doctor, based on years of experience, says, I believe you have an 80% chance of a full recovery, right? This is saying without any medical diagnosis. To check your understanding, please try these two problems, right? 1, 2. This is session summary or recap, where the classical approach defined by this formula is simple but requires two things: equal likely finite outcomes, right? The frequency approach, which is given by this formula, is based on long run observation and experimentation. The axiomatic approach provides the fundamental rules: non-negativity, certainty, additivity, that all probabilities must obey. From this we derive powerful theorems, right? The subjective approach quantifies personal beliefs, experience, or opinions, right? Thank you. Oh.